And we will do a screen share here. And go back to notes. The bonding notes, you guys can tell we're doing gas laws. Okay. New note. Today's 22nd, right?
Yep.
All right, excellent. Okay, so buffers, that's where we are. But first of all, what do we need to think about in terms of class tomorrow? So what's due? So we got a homework, right? And I think we'll have a quiz, which will obviously be on some aspect of acid-base stuff. Probably the stuff after pH and such. We did sort of the earlier side of the chapter on last week's quiz, so we'll sort of focus on the later side for this quiz. And your homework comes in tomorrow. No lab due tomorrow because we're finishing up the kombucha lab. So basically, whoever did the 4 titrations last week will do the pH meter titration and vice versa. So we just swap you this time. All right, so we were talking about buffers here, guys. Now, what did we say about buffers last time? I'm not going to rewrite it. But basically, we had 2 definitions for a buffer, right? We had the actual working definition of the buffer. And we said that essentially a buffer is a solution that will resist a change in pH if you add an external acid or base to it. Okay, and we talked about why that's important. For example, buffering at physiological pH in a cellular system or even our human body or whatever the case may be, so that all those biological reactions that allow us to live can do what they need to do without the enzymes basically becoming denatured. So that's the working definition of the buffer. Then there's the chemical definition of the buffer, and that's the one I kind of want to focus on here. So if I have a buffer, I can actually just put it down here. There's 2 ways I could represent the buffer. It's always going to be a mixture of a weak acid and its conjugate base, or a weak base and its conjugate acid. So it's always going to be a mixture of a conjugate acid base pair. Okay, so one option would be to have a weak acid and its conjugate base. So we could have, for example, a acetic acid. That's a good example of a weak acid. Sodium acetate. So I'll just put the acetate ion there. Okay, so there you go. So you've got a weak acid and its conjugate base. All right, so that would constitute a buffer. What's the other option that we could have? Well, we could have a weak base and its conjugate acid. So a classic example there would be, for example, an ammonia buffer. So that would have NH3 in it. And then you'd have a mixture of that conjugate acid, which is NH4 1+. So we would introduce that as like ammonium chloride or some salt like that. All right. So there are 2 classic examples that we can go at a buffer really from either direction if we want to. Now, let's just sort of focus on that acetic acid sodium acetate buffer. Okay. So for a buffer to work, the primary thing, and I'll go ahead and write the dissociation equation to show both species in solution. And what we'll make is the acetate ion. And of course, we'll have hydronium ion in there. Okay, so that's a familiar equation to you guys at this point. Now, for a buffer to work, we have to have both of those species present. So like I said, we would probably introduce that as the sodium salt, because we can go to the stockroom and get that, right? We can get sodium acetate or potassium acetate out of a bottle, and we can dissolve it in solution to give us acetate ion when it dissociates. But the idea here is that we want to have a large excess of both of those components relative to any acid or base that we add to this thing. So in other words, you know, we maybe want this to be up around 0.5 molar. And then to have a perfectly good buffer, we'd want the conjugate to be there at a very similar concentration. It doesn't have to be exactly the same, but they have to be essentially similar. Okay. So you can see now that we have a large excess concentration of both components present in the solution. All right. Now, does that make sense to everybody? All right. So here's another thing we have to think about. Keep in mind, of course, that we're going to add both of these things as the acid and the conjugate base. And then, of course, each one is going to go through its own acid-base dissociation reaction. So remember, I've got the acetic acid here going to hydronium, but I could also have the acetate going back to water, right? So in this case, do we really think about that as being a primary reaction that's happening here? In other words, if I add 0.5 molar of the acetic acid, what do you think the equilibrium concentration is going to be? Something really small like 0.05 or closer to 0.5? What would you guys think? In other words, would that acetic acid concentration be much different than what I'm showing you right now at 0.5 molar if I let this thing dissociate and make an ice table out of it?
No, it should be relatively similar to what it is here because we have a low K.
Yeah, so we got a small Ka, right? Somewhere on the order of 10 to the -5th, right? Well, and then there's the other thing going on here. Notice that I've got the common ion in there, right? I've got Le Chatelier's principle playing a role here, don't I? So I've got the dissociation product, which is the acetate ion. So that's like adding a product, isn't it? So what does Le Chatelier's principle tell us about that? Well, if I do that, that's going to force the reaction back to the left, isn't it? Because I added a product, in this case, what we call the common ion, which is going to be the ion of dissociation of the acetic acid. Okay, so that's going to inhibit the dissociation of the acid as well. So what that means, and I could say make the same argument for the acetate, right? Because this is a reversible reaction. The acetate's not going to dissociate much back to acetic acid because it has a very small Kb associated with it, but also the fact that I've got 0.5 molar acetic acid in there. So I've got the product of that dissociation sitting there already. So what that really means, and this is one thing that your author likes to emphasize, is what you mix is what you get. In other words, if I make this up to be 0.5 molar in each of these components, the dissociation of each is so small that I can pretty much take it to the bank that it's still going to be 0.5 molar in solution before I do anything else to the solution, right? So there's really literally no dissociation to worry about. Okay, so we'll put that here. What you mix is what you get. I kind of like that. He has those little witticisms in there. So if I make my buffer up to be 0.50 molar in each component, it's going to be 0.50 molar in each component. I don't really have to worry about it dissociating. And you could do the ice table problem to show that, okay? To show that the 0.5 molar for all practical purposes is still 0.5 molar on both sides. You know, it's kind of an interesting little problem to do. All right. So ultimately, when I do buffer problems and I go to a target concentration of both components that I add in there, well, that's going to be the concentration I'm going to use in subsequent calculations. Okay, so that's basically why I need to keep that in mind. All right, any questions so far, guys? Okay, so now we get to talk about buffer calculations. Now, as it turns out, you know, I could calculate the pH of this buffer using standard ice table techniques. I mean, you know, you guys want to do that? I mean, we could do it. I mean, I think you guys all know how to do it, but we could do it if you want to. Okay, so it's totally up to you guys. In other words, using techniques that you already know, if I'm talking about the buffer I just set up there between the acetic acid and the acetate ion, could you calculate the pH of that solution? How would you do it?
Set up an ice table with, we're gonna cross out water, but our acetate ion, our our acid and then hydronium are all factors, and we just use our Ka.
Yeah, well, let's just set it up here. I'm not going to rewrite the equation, but let's just set it up and see what's going to happen here. Okay, so initially I've got 0.5 molar of that guy. I've got 0.5 molar of that. Water, you said we're going to cross out, right? How about the hydronium ion? We have to assume no reactions happened, right? So what are we going to put there?
0.
0. Yeah, so we'll put a 0 down there for hydronium ion. Which direction does the reaction have to go? Left or right?
Right.
Yeah, because I got to make some hydronium, right? So in other words, my Q is less than, my Q is 0, so it's less than my K. So I got to go to the right. So I'm going to lose some of my acetic acid. I'm going to make X of my acetate, and I'm going to make X of my water. So 0.5 minus X. Oh, add down, you get 0.5 plus X for the acetate, right? And then you get X for the hydronium ion. Okay, plug it all back into the law of mass action, right? So that's products over reactants. So that's going to be what? 0.5 plus X times X over 0.5 minus X. And all that's equal to, what is it, 1.78? Somewhere like that, times 10 to the minus fifth. I think that's right. As long as you see it as 1.8 times 10 to the minus fifth, but I think that's right for acetic acid. Hey, how can I simplify this to keep this from getting all quadratic on me?
Get rid of the X in the denominator.
Yep, I could certainly do that. See any other X's I can get rid of?
On top, the X with the X plus 0.5.
Yeah, any additive or subtracted X's I can get away with getting away to throwing away. And again, I know that because my Ka value is really tiny compared to my initial concentrations. So I'm going to certainly be okay with the 5% rule. So what ends up happening? The math is easy now. The 0.5 cancels with the 0.5. And what I get is X is equal to 1.78 times 10 to the minus fifth molar. And that's equal to the hydronium ion concentration. Okay. So now what's my pH? What's the negative log of that? Anybody got the number? Should still be acidic. It's just not going to be very acidic.
I got 4.75.
Okay, and we could throw one more sig fig on there if we had it.
4.7. Sorry, rounding 4.750 then.
Close enough. Okay, so a little bit acidic. All right. Now here's the question: if I didn't have that acetate ion in there at 0.5 molar concentration, would the acidity have gone up or gone down? In other words, what would the pH have done? Would it have risen or fallen? If I didn't have the 0.5 molar acetate in there. Just think about it from the point of view of Le Chatelier's principle. If I didn't have that common ion in there, would the reaction go further to the right or further to the left?
I feel like it would go further to the right a little
Yeah,
bit.
it sure would. Yeah, we go further to the right because the common ion is not there to resist the dissociation of the acetic acid. So as a result, the solution would be more acidic and the pH would drop. Okay. So we could go ahead and do the calculation that way. Now, here's the shorthand way of doing it. Okay. What we're going to do is we're going to come up with a nice shorthand equation so we don't have to go through all the equilibrium. And the shorthand equation is called the Henderson-Hasselbach equation. I think I spelled that right. It's like Henderson-Hasselbalch, but they say Hasselbalch. All right, and here's what we do. Basically, we're just going to start, and I'll just do it for a standard weak acid. So it'll apply to any weak acid, but here's a generic weak acid, HA. Okay, it's associating in water, same reaction you guys have seen a zillion times, and it's going to have a Ka associated with it. So you're going to make the anion of the acid, and you're going to make hydronium ion. Okay. Now, can you write a Ka for that? Sure you can. In terms of the law of mass action, Ka is products over reactants, right? So it's going to be the A1 minus, whatever its equilibrium concentration is, times the hydronium ion concentration at equilibrium divided by the HA. That's the original acid. And that's its equilibrium concentration. Okay, so we're going to do some math on this. So what we're going to do is I'm going to take the negative log of both sides. We've done this kind of thing before, so you've seen it before. Now what we're going to do is we're going to use that log rule. Remember where I can say that the base 10 log of AB is equal to the log of A plus the log of B. Remember seeing that? So I'm going to use that here. Okay. So I'm going to distribute that log throughout and break those two terms up on the right. So that's going to be equal to the negative log of the ratio of A minus over HA. You'll see why I'm pulling the other term apart, plus the negative log of the hydronium ion concentration. Oh, why did I do that? Well, what's another name for the negative log of the hydronium ion concentration?
pH.
pH.
That's pH. Yeah, that's pH. Okay. So what I'm going to do is I'm going to just rearrange the equation here. Okay, so I'm going to leave that negative log over on that side. So I'm going to say, all right, I got minus log of the Ka is equal to positive log, right? So I'm moving that other log term to the other side. A minus or HA. I see another way I can actually simplify this too. Okay, plus the pH, right? What's another way I could simplify this if I wanted to on the left? What is another name for negative log of Ka?
Ka.
Not Ka, you're close. What do we do to the negative log of the hydronium ion concentration? We called it what, a pH? So if you have a negative log of a Ka, what do you call that?
pKa.
pKa. Remember, you see the negative log, that means P, or P means a negative log. All right, so now I'm just going to rearrange this a little bit. So now I can say that pH, because that's usually what we're solving for, is equal to the pKa, just taking that to the other side. Actually, would that work out? How did I end up with a pKa over on that side? It is positive. What did I do? Oh no, I'm good. It's on the correct side. Yeah, I'm moving the other term. Sorry, I'm taking that over there. Okay. Well, that didn't work out sign-wise. It's fine. pKa plus base 10 log of A minus over HA. Okay. It's called taking a wrong turn when you do your algebra. There you go. So this thing here is the Henderson-Hasselbach equation. All right. Now, again, what does it mean? Well, what it allows us to do is to calculate the pH of a buffer that we can prepare using a certain concentration of the anion of the acid and the weak acid. In other words, the conjugate base of the acid and the parent acid. And remember, I don't have to worry about those concentrations being dissociation products. If I put 0.5 molar in of A minus and 0.5 molar in of HA, that's what I'm going to stick into the Henderson-Hasselbach equation. Because remember, what you make is what you get, or whatever I said. Okay, so we don't have to worry about those guys dissociating. What's the other piece of info we need? Yeah, we need the pKa of the original acid, but we can go look that up, can't we, or calculate it from a Ka. So basically, there's two ways to use this thing. If you know A minus and HA and you know a pKa, you can calculate a pH. The other way to go about this is if you have a target pH and you know a particular acid you want to use and you know it's pKa, you can get the ratio of A minus to HA to satisfy that equation, that pH. And then if you know what your total concentration of the components are, you can then do a little bit of algebra to figure out what A minus and HA actually are. Okay, so those are the two ways we would use Henderson-Hasselbalch. Now, the other thing you might say is, well, wait a minute. This looks like it works for an acid, but what about a basic buffer? What if I had this situation? So I have a weak base reacting with water. And what do we get? Well, we end up getting the conjugate acid, HB, or HB plus, right? Plus hydroxide. That's a weak base dissociation. And that's, of course, going to be defined by a KB. Now, if we wanted to, we could actually derive a form of Henderson-Hasselbalch in terms of POH and KB if we wanted to do that, but we don't have to. The nice thing is regular old Henderson-Hasselbalch works, okay? So if I were to rewrite it, this same equation is actually going to work for the weak base dissociation because we still have a conjugate acid base pair. And the base part still goes in the top. In this case, I guess technically we should, why don't we just go ahead and call it what it is? That would be the base. And then HB plus, that's the conjugate acid. That would go on the bottom because that's the conjugate acid part. And now, what would the pKa refer to? It would be refer to the pKa of the conjugate acid. And chances are that one you're going to find in a table, right? At least the way Harris actually sets things up. So the nice thing about this is you don't need two forms of Henderson-Hasselbalch. The same form works for both an acid buffer and a base buffer, okay? Just remember the pKa always refers to the pKa of the acid part of the buffer, regardless of whether it's a basic buffer or an acid buffer. Okay, so it's one size fits all, which is actually really, really nice. All right, so any questions so far about Henderson-Hasselbalch? And again, we're going to show you how to use it here in a little bit, but I just want to make sure, and you don't have to memorize how to derive it or anything like that. It's just kind of nice to know if you like those kinds of things, but you do want to remember the useful form of the equation. All right, so here's the other thing. There's a special case, and it really kind of comes back to the problem we set up. That special case is when the acid part of the buffer is equal in concentration to the base part of the buffer. Should have made that A minus. There we go. When the acid part of the buffer is equal to the base part of the buffer, when those two concentrations are the same. Now, take a look at what happens when I plug the same number into Henderson-Hasselbalch. So we could do it for example, our original question. We can say that pH is equal to pKa plus the log of, what was it, 0.5 molar over 0.5 molar. That was our example we did, right? And we can calculate the pKa, right? pKa is just equal to the negative log of, what was it, 1.78 times 10 to the minus fifth, which happens to be what? What'd you get when you take that negative log?
That would be 4.750.
Sounds familiar, doesn't it? Okay. Now, what happens to the log term? So when you get
Equals
0.5,
zero.
yeah, when you get 0.5 over 0.5, that's 1. And if you take the log, base 10 log of 1, that's equal to 0. So that whole term goes to 0. So in that specific case, the pH is equal to the pKa, which is equal to 4.750. Now, is that what we got before when we did the full on equilibrium approach? Yeah, 4.750. So see how we put a nice table together and got the pH? And then I applied Henderson-Hasselbalch down here, got the same thing. Okay, and that's exactly what should happen. All right, so notice how Henderson-Hasselbalch is kind of a shortcut for a buffer that kind of takes the equilibrium step out, so you don't have to worry about doing it. All right, does that make sense to everybody?
Yep.
Okay, good. So of course we can have buffer problems where those two concentrations are not equal to each other, correct? So they can vary a little bit. Now we don't want them to be massively different from each other, but I had to have a situation where say the base is 0.45 molar and say the acid part's 0.55 molar. Okay, then what happens? Well, then the log term matters. I can't get rid of it. I actually have to calculate out that ratio and take the base 10 log of it. And then that has to add to the pKa. Okay, so that can happen as well. All right, so let's just take a look at a simple example of Henderson-Hasselbalch so we can just sort of make sure we understand how to utilize it. So here's example number 1. I don't think I gave you guys these, so I'll write them out. I want to know the pH of a buffer prepared by mixing . 0.150 molar NaH, NH3, sorry, and 0.258 molar ammonium chloride. All right, so when I say mixing those are going to be the final buffer concentrations as opposed to initial concentrations. Okay, so in other words, we don't have to worry about doing a dilution or anything like that. Those are going to be final concentrations of NH3 and ammonium chloride in the solution once we've prepared the buffer. So we know what those are. All right, so first of all, I can use Henderson-Hasselbalch, right? I want to get the pH, so let's write Henderson-Hasselbalch out. So pH is equal to pKa. In this case, it's in terms of, we can write it over base over acid. So if we really want to be really generic about it, I could do it this way. It's the concentration of B for base over the concentration of A for acid. So it's the base part over the acid part. So that's the most generic way I could possibly write Henderson-Hasselbalch, right? Now, if I wanted to, I could go ahead and recognize that the ammonia here is the base and the ammonium, which of course is the conjugate acid of the base, will be the acid part. All right, so let's see here. What do I need? I need a pKa, right? So what would that be the pKa of? What ion would I look up?
Ammonium.
Yeah, I need the pKa for ammonium, so it's for NH4 plus. Unfortunately, that's going to be found in your appendix in your book, so your Ka appendix, appendix B or whatever it is. And, you know, you can look that up. Now, I think I have it in terms of a Ka. I mean, it's actually right there. It turns out that it's equal to 9.245. But let's say you only had a Ka. So another way to calculate it is you could take the negative log of the Ka. So I can look up the Ka, and that's 5.69 times 10 to the minus 10th. So that's my Ka value, which I can also find in the table. And that turns out to also be 9.245. So either way, you can look up the pKa directly, or you can calculate it from the Ka. Okay, now I got everything I need. Now keep in mind, this is where I'm actually using this as applied to a base buffer. Okay, so what I can now do is go ahead and make my substitution. So pH is the pKa 9.245 plus the base 10 log of the base part, which is the ammonia 0.150 molar divided by the acid part, which is 0.258 molar. Okay, and when you work all that out, you get 9.245, and I'm just checking, making sure I get my numbers right. And then when you take that I'll just write it out to what the calculator told me. It was 0.2355528. Okay. Now, remember, if I take that ratio, it's going to still be around 0.1 or something like that. And then when you take the log of it, it turns out you don't actually end up picking up another sig fig when you take that log. So you're really only good to the thousandths place there. So now when I work that out, you end up getting 9.009 for the pH. And it's a basic pH, and that's exactly what we'd expect because it's a basic buffer. We made it from a weak base and its conjugate acid. Okay, so keep that in mind. A basic buffer made with a weak base and its conjugate acid will have a pH above 7, but an acidic buffer made from an acid and its conjugate base will have a pH of less than 7. So a lot of times when we're doing these kinds of problems, one of the things you have to ask yourself is what's an appropriate conjugate acid base pair to choose? Okay, so obviously if you're trying to get an acidic buffer, well, you wouldn't pick a ammonium pair because that's going to give you a basic pH. Okay, and also as a general rule, you're trying to also find something that has a pKa close to the target pH of your buffer. Okay, because what that means is you don't want that log term to get too out of whack. You want it to be as close to 0 as possible. So you're always trying to pick a pKa that's close to the pH that you're targeting. All right, so far so good, guys. So that's just plug and chug. Any questions at this point?
Nope.
All right, good. So next thing, we could ask, how does a buffer work? How does it do its job? All right. Now, remember, if I make a buffer, we have to remember what the components of the buffer are. It has two primary components. You got a weak acid, and you're going to have a weak base. All right. Now, the other thing it's important to remember is that you have to have a large excess of both relative to whatever you're going to add to the buffer that might change its pH. Okay. Now, here's the deal. If I add a weak acid, what's that going to react with? Well, the acid is there to react with any added hydroxide or base. Now, if I have a weak base in there, what's that going to do? Well, that's going to react with any added hydronium ion that comes from an acid that we might put in there. Okay, so the point is, I've got something in there that can react with either a base that I add or an acid that I add. And normally when we talk about adding an acid or a base to a buffer, we're talking about a strong acid or base. So in the case of a strong acid, it's something that dissociates 100% to give us hydronium. Or in the case of a strong base, it's something that dissociates 100% to give us hydroxide. Okay? So could we actually write the equations for those reactions in terms of the acid-base chemistry? Sure, we could. So let's say I've got my weak acid. We'll just call that HA. All right, that reacts with the hydroxide that we add. Okay. Now, what have we got here? We have a weak component added to a strong component. What do we know about weak plus strong from last week, guys?
They disassociate 100%.
Yeah, it goes 100% to the right. So in other words, it has a really huge K, right? So that means really when I have a situation like this, I can use a single arrow, can't I? Because I have a really huge K. I don't have to worry about that. So what's going to happen? Well, the acid's going to protonate the base. We're going to make water. And I'm going to be left with the anion of the acid, which is the conjugate base. Okay? Now, what is that? Well, if you look at that in terms of a K, that's 1 over the KB for the A- species. And if KB is a small number, then this is going to be a very, very, very large number. Okay, so that's why the reaction goes 100% to the right. Okay, what if we did the alternative here, which is the weak base, which I can just call A minus. So if it's a conjugate acid base pair, we'll call that A minus as the weak base. Let that react with hydronium now. Okay. What have we got? Again, a situation where I have a weak base reacting with a strong acid. Weak plus strong does what?
Dissociates
100% to the right. So what am I going to make? I'm going to make the conjugate acid back again. That's the HA. And I'm going to be left with water. Okay, what's that? That's 1 over what?
Ka.
Yeah, it's 1 over Ka for that weak acid. And if Ka is a really tiny number, 1 over Ka should be a really, really big number. So that's also going to be way bigger than 1. Okay, so that again tells me that my reaction for all intents and purposes is going to go 100% to the right. I can treat it that way. I don't have to utilize equilibrium here. Okay, so what's actually happening? Well, remember that I have that ratio of base to acid in there. And what I make is what I get until I add a strong acid or base to it. So if you think about it, what's happening? Well, what I'm doing when I add, say, an acid or a base is that I'm actually chewing up some of the original weak component and I'm making some of its conjugate. So what does that do? Well, that starts messing with that ratio. That's the argument of the log term, right? So let's just write that ratio out. So I've got the log base over acid, so I can do it in terms of this. It would be my A minus over my HA, right? Okay, what if I add acid to this? When I add acid, I really mean I'm adding hydronium ion to it. What's going to happen? Well, I'm going to chew up some of the A minus, right? So this guy decreases in concentration. Well, what happens to the HA?
It would increase, wouldn't it?
It increases. Yeah, exactly. Take a look at that bottom reaction. It increases. So what I'm doing effectively when I add an acid or a base to this is I'm actually monkeying around with that ratio in the log term. Okay, I'm changing that ratio. And here's the deal. Does that really matter that much mathematically? Because what am I doing? I'm adding that log term to the pKa, right? The pKa is constant. That's not moving. But what does a log do? So if I take a ratio, right, and then I change that ratio a little bit and take the log of it, what does the log physically do to that number?
It raises it to the 10th power.
Well, it's kind of the opposite of that, right? So it compresses it. An anti-log actually raises it. You're taking a log, it actually takes it in the other direction. So I'm taking that ratio and I'm actually compressing it. I'm making it smaller. So then when I add it to the pKa, it doesn't matter as much, does it? So ultimately, even though I'm changing that ratio by adding an external acid or base, I'm really not changing the pH that much because the log of that ratio is being compressed mathematically. Okay, so it becomes a fairly small number when I add it to the pKa. So that means the pH doesn't change very much. So from a mathematical perspective, that's pretty much telling us how a buffer works. Okay, and I like to think of it from a mathematical perspective like that. It just kind of makes sense to me. All right. Now, where would the tipping point be though? Where would I get into trouble if I use that argument? Can you
Isn't it
imagine?
the same way with the other one? If you would add too much acid, it would go basic because the calculations would go wrong.
Yeah, it'd be the same thing. But yeah, if you added the acid, so you said add acid, right?
Yeah.
Okay, well, that's kind of what we did in this example. What if I added a base? Well, HA would get smaller, right?
Yeah.
And A1 minus would get bigger. So the log term would actually get a little bigger because that ratio is getting bigger. Okay, but it would still be compressed. But what would happen? Here's the tipping point. What would happen if I had, say, 10th molar of each one of those things to begin with, but I added 0.15 molar of, say, acid or base? What would happen? What if I added an excess of acid to my buffer? Well, think of it as a limiting reactant problem. Go back up to this second reaction equation. What if I had 10th molar of this, but I added 0.15 molar of that? What would happen?
You're just going to have acid at the end. And so your equation's going to break down because you don't have enough buffer to react with your hydronium.
That's exactly right. Yeah, basically you run out of the base part of your buffer, don't you? And when you run out of the base part of the buffer, then what's going to happen? Well, you're going to have excess hydronium in there. What's driving the pH at that point?
The hydronium.
The hydronium, because it's the strong thing. Exactly. So that's what we refer to as buffer capacity, or the capacity of a buffer. So that's why, remember, I told you want to have a large excess of both of those buffer components in there relative to the concentration of the acid or base that you're going to put in there, because you don't want to get to that point where you exceed the capacity of the buffer by breaking it down, by using up either all of one weak part or all of the other weak part. Because once that strong thing goes into excess, that's driving the pH. Okay. So we have to be always aware of that. We always have to watch that ratio and see how much of any given component that we're actually using up. And you'll actually see this. You'll get to a point in dynamics where you guys start doing titration problems. It'll be later in the semester. And you'll get to a point in the titration where you've actually added enough of, say, the strong component to react with all of one of the weak components. And then what you'll find is there's really no equilibrium to calculate, or even a Henderson-Hasselbalch to calculate, because it's just a limiting reactant problem, and you just calculate the excess ion at that point and you're done. Okay. So it's kind of important when you work these kinds of problems to recognize what you've actually got in solution. So let's start an example. Okay. So this kind of shows where we can take a problem like this. All right, so I'll just write it out as I have it. It's what would be the pH of the buffer in example 1, the one we just did. If 50 mils of 1.00 molar HNO3 nitric acid were added to it. So in other words, I've got a buffer and I've set it up, but now I'm going to add some acid to it. Okay. So what's the reaction? Well, the reaction is going to be that strong acid reacting with the base part of the buffer. But the first thing we have to remember when we're dealing with this is that HNO3 is a strong acid, right? So if I've got 1.00 molar, let's go ahead and just write the reaction showing its dissociation. So HNO3, we'll do it as a Bronsted-Lowry dissociation here. Do I need a double arrow or a single arrow?
Double.
Would I? What kind of acid did I say that was?
Nitric's is strong.
Yes, we get 100% to the right. 100% dissociation, right? So we're going to make hydronium. And I'll also end up getting some nitrate ion. Okay. Now, here's the deal. If I've got 1.00 molar of that, and I got 50 milliliters of it, the question that I could have is how many moles of acid would I have over here? Okay. Now there's a reason why I'm doing this. Well, we know how to do it, right? Molarity times volume gives us moles, doesn't it? And then I can have a mole bridge that takes me from here to here. And we can see we'd have an equivalent number of moles of hydronium ion because of the 100% dissociation, correct? So we'll just go ahead and do this. Let's see, that's 50 milliliters. I could do it this way, 50.0 milliliters. And then remember, I can show molarity as millimoles per milliliter. Remember when we did that? It's just nice when you're using milliliters to do that. So you get what, 50.0 millimoles. If I want to turn it into moles, I could do that. I just take that three places to the left, you get 0.050 moles of H3O plus. I think I did that right. Yeah, and get another sig fig in there. There we go. So everybody okay with that? I just calculated the number of moles of hydronium that I got from the dissociation. I didn't even put the mole to mole relationship in there because we know it's 1-to-1. Some point as chemistry majors, we can just kind of see that stuff. All right, so here's the deal. As I said, what's the actual reaction that goes on? What's the hydronium going to react with when I add it to the buffer? So you have to go back to that problem. What buffer did I have in example 1? I think it was an ammonium buffer, wasn't it?
Yes.
Yes. So which component is the hydronium going to react with?
The ammonia.
Ammonia, that's the base. Yeah, so it's always the acid reacting with the base. So it's the NH3 plus the hydronium ion I'm putting in there. Okay. All right, what have I got? I've got a weak plus a strong. What do we know about weak plus strong?
100% to the right.
100%
Single arrow.
to the right. Yes, 100%. What am I going to make? I'm going to make some water. And I'll also make some NH4 ammonium ion. Okay, make sense? Now, I could verify that because that's 1 over the Ka for ammonium. And that turns out to be a huge number, which you could go verify if you wanted to. All right, but here's what we often do. Once we set up this, what I want to do is kind of set up a precondition, if you will, to sort of show what's going to happen in terms of the moles in this. Now, we can do this by just basically writing this as a limiting reactant thing. But in many cases, what we find when we've got this simple 1-to-1 stoichiometry is we can set this up like an ICE table. But instead of calling it an ICE table, I'm going to call it an ICF table, but it works the same way. F now stands for final concentration, which is telling me there's no equilibrium involved. Okay? So now, if you go back and you look at what we've got, the hydronium ion I can stick in here is 0.0500 moles, right? These are moles now. Now, how about the ammonia? Can I get the moles of ammonia? Let's go back and look at that problem real quick. All right. I think I can because I've got a molarity for the ammonia, okay? Now, it doesn't tell me what volume I've got it in. So what can we assume about the volume if I don't tell you?
A liter?
Yeah, we're going to assume it's a liter. So if I got a liter, how many moles of ammonia are in here?
0.150.
0.150. Yes, sirree. I'll just write moles up here. Water, we don't worry about, right? We never do. Is there any ammonium in there? Yeah, there is because we made the buffer, right? So if we go back up here, oh yeah, in 1 liter, I've got 0.258 moles of ammonium. So that's in there. I got to put that in there. All right, who's my limiting reactant? Oh, it's the hydronium. So I'm going to lose that amount on both ends here. I'm going to make that amount over here. Okay, so that's gonna give me 0 down there. Then if I do that, I get what? 0.2, is that right? Or is it 0.1? What do I get? 0.150 minus, yeah, it should be 0.1. And what do I get here? 58, so I end up getting 0.308. All right, so this is where we're gonna end, and we'll pick it up here on Wednesday, but the point I wanna show you is, yes, I added some hydronium to the buffer, but do I still have a buffer?
Yes.
Yes, because I've got some of my base part and I've still got some of the acid part, don't I? I changed the ratio a little bit, but I've still got them both there. So this thing is still acting like a buffer. So what do you think the next step I would take would be to calculate the pH of the buffer, or that I have now after adding the acid? I've still got a buffer, so how would I calculate its pH? What would I do? Two things. I could do it two ways.
Would you use the Henderson-Hasselbalch?
Yes, I could do that because I got a buffer, right? So that would be the fast way to do it, is to just use the Henderson-Hasselbach equation. What's the other way I could do it?
You
Well, I
could do
could
it
just set
the
it-
long way.
I could do it the long way with equilibrium, where I could just set it up either in terms of the NH3 reacting with water or the NH4 1+ reacting with water, and either using a Ka or a Kb and then sticking those values back in. The only other thing I'd have to do there, though, is I have to turn them back into concentrations, because that's what we use in ice tables. So I'd have to, assume that there was no change in volume, or if I did have a change in volume, I'd have to do a dilution. Okay. But as it turns out, there's actually a nicer way to do it. And we'll come back and do that on Wednesday. Everybody good? All
Yep.
right. Everybody ready for lab tomorrow?
Yep.
Most
All
part.
right. Awesome. We'll see you guys then.
All right. Have a good
Have
day.
a good day.
You guys too.